All right, thank you everyone for letting us present from video. Noah and I are out in the field installing groundwater wells, and so on the same notion, this presentation is about real-time monitoring of groundwater pollution caused by fracturing wells, hydraulic fracturing wells. It's a review of some of the methods and discussion by Steinbeck and Lockwood in a white paper that focused on surrogate monitoring of these pollutants that are associated with oil and gas production sites. So what is surrogate monitoring? Surrogate monitoring, or SM, is an auxiliary method used to measure an analyte continuously that otherwise might not be possible, such as something that's very expensive, or perhaps you're at a field site that's far away from a lab, or again with the real-time notion, perhaps only periodic sampling of the actual analyte is available, whereas cheaper, lower cost sensors can be deployed and measure continuously through time for a better understanding of what might be going on in the subsurface and groundwater. It's useful for groundwater contamination in this essay in context to high salinity fracking fluid, and then also dissolved methane leakage, perhaps from a casing or the fractures themselves up through geologic strata. So the pollutant and the associated surrogate measurement that this paper discusses, aquifer contamination by fracturing fluid, and they use conductivity and TDS as surrogates, and then methane leakage to the aquifer due to the fracturing or case breakage. They look at oxygen reductive potential or dissolved oxygen. So what are some of the benefits that are discussed in this paper for surrogate monitoring, and as well some other literature that I looked into? For one, as previously said, it reduces laboratory analysis costs. These are low-cost surrogates that can be deployed real-time and give information on what's going on in the hydrogeologic system continuously. And furthermore, they yield a comprehensive set of information for management decisions. So whereas you might have periodic measurements from a more expensive method, this gives you a continuous method potentially to catch abrupt changes in concentrations or water quality. An example is using conductivity and temperature to measure chloride. It's been well tested and reasonably accurate manner of using surrogates to assess water quality, and tends to be cheaper. These two sensors, conductivity and temperature, are cheaper and more readily available, abide to a lot of EPA regulations, more so than some of the more expensive chloride sensors. So how does this essay discuss and implement surrogate monitoring? One of the sensors they're working with is conductivity and temperature. So conductivity is the dissolved ion concentrations, which subsequently are proportional to the measured change in electrical flow between two metal electrodes, platinum, silver, nickel, etc., different types. You can see this diagram here simplifying the internals of those types of meters, where the sample waters are allowed to flow through, and the sample waters represent the electrolyte bridge of those dissolved ions to transfer the electrical flow between those electrodes. Temperature is another surrogate that they discuss, and it's done, or it's measured by using a thermistor, which is a resistor of or a promoter of electricity. Its impact on the electrical flow is proportional or in relation to the ambient temperature of the sample that's being measured. It can go both ways. In this diagram, resistance decreases with increasing temperature, but depending upon the design of the thermistor, it can be inverse, where an increase in temperature rises resistance. And then conductivity and temperature are correlated. Several documents discuss this by combining the two. It allows for estimations of attributes with reasonable accuracy of TDS, accuracy dependent upon the device in use, but TDS, total dissolved solids, and also salinity with algorithms specifically designed for the different devices used. Oxygen reduction potential, or ORP, it's a measurement by an ISE and made in tandem with pH to quantify the flow of ions and or electrons through a solution. So this is kind of an interesting setup. There's a bridge that is made, a semi-porous bridge between two electrolytes, And within each of those electrolytes, there's a special metal electrode, and that electrode enables a potential difference for the transfer of hydrogen ions. And so the measurement you can see in the bottom is kind of a zoom in of the conceptual diagram at the top. But the main difference is the voltage offset between the two metals used to differentiate between pH and ORP. Dissolved oxygen. The previous presentation that Lily allowed me to give to everyone, I discussed this a little bit. Two types currently used, chemical and optical. There's a couple different types of chemical as well, but in this case, just giving a simplified diagram here on the right. The chemical dissolved oxygen is usually measured with a unique metal, gold or platinum cathode, and silver anion electrode. And again, it's much like an ISE. The electrolyte solution between the electrodes lets the sample permeate through, and it allows the measurement based off of the oxygen concentration to the current between the two electrodes in the solution. This is again something that requires replacement often, but is relatively cheap to replace those devices, especially for a larger environmental consulting company, or perhaps economic geology resources. Maybe on the wellhead they have these set up around the base station of the actual fracking head. So optical DO is a little bit newer method, precision equivalent, but also much more simple in terms of the device's upgrading. It uses a blue LED tuned to a specific wavelength that hits a photon sensor, and that excites that sensor to produce red emission. And the amount of O2 in between that red emission and photodiode sensor is proportional to the concentration of oxygen in between. In terms of longevity, optical DO is discussed as having a much longer life in unattended, that being unattended typically is a description of continuous measurement in the field, versus the chemical DO that might need to be replaced often due to fouling of the cathode and anode and electrolyte. So some of the details they give about dissolved oxygen sensors in terms of making the decision between electrochemical or an optical, they're shown here. EPA doesn't necessarily have approval for optical just yet because it's a newer technology, so it hasn't undergone the rigorous extent of analysis in the field. However, DO for electrochemical is EPA approved. And mentioning again the maintenance associated with the electrochemical is greater than that of the optical. Cost for optical as a new technology tends to be greater than electrochemical methods. And you can see a diagram on the right there about the proportionality of dissolved oxygen and temperature. So with an increase in temperature, the amount of dissolved oxygen that can be readily increase in concentration actually decreases. So lower the temperature, the increase in concentration of dissolved oxygen. And then they give a nice summary of some of the best suited applications for the different types of electrochemical versus optical, shown there on the bottom right table. So some of the results of their analysis of these different methods, the ORNP, dissolved oxygen, conductivity, and temperature, in terms of an assessment of laboratory and field observations of fracking fluid. So the correlation of conductivity with increasing volumetric weight percent of fracking fluid here is shown, and there's a pretty clear correlation between TDS, specific conductivity, and then also chloride-derived salinity. Similarly, ORP correlation with rising methane output. So as methane output increases, the oxygen reduction potential of solution decreases, and the trend slope for that decrease is rather rapid. There's not a whole lot of difference shown here between the 1 liter per minute versus 1.5 liters per minute production of methane, but there's a clear distinction difference between the 0.5 liters per minute versus the 1.5 liters per minute methane leakage per time. So one thing that's to be considered here perhaps is that maybe it's more of a warning indicator as a surrogate monitoring tool, ORP for methane, versus an explicit quantification of what might be going on, kind of more of a signal to then go out and grab samples and take them to have a more accurate and robust laboratory analysis made. More correlation with increasing rates of output of methane. Here, instead of ORP, using DO, so dissolved oxygen concentration. You can see here the trend for all 3 different rates is relatively similar. So as said with ORP, it's more or less a flag to indicate that there might be leakage. Again, you'd have to correlate this maybe with some other attributes of the system, such as microbial activity and other things like that, where DO decreases because of perhaps some kind of microbes or algal blooms. But in this case, it does give a flag suggesting that with the presence of or increasing amount of methane gas dissolved into the waters, so too the dissolved oxygen concentration drops. So some of the measuring equipment that they discuss, and then I also grabbed the specifications of another meter. This paper discusses using the Troll 600 there, the yellow columns, and the other device that I looked at is called an XO2 by another manufacturer. So these are two, I don't know if you would say competing, because they're both interested in environmental resource, but they're both developing new equipment to get a better market share, but collectively it's a noble pursuit through these manufacture of these useful tools. You can see some of the comparisons between the range, accuracy, response, and precision. As far as cost difference is substantial between the two. It's about $3,000 more for the Troll, but it also bears with it a bit better improved values of range, accuracy, response, and precision for most of the values shown. So that kind of sums up what I dug into this paper. I'm looking forward to maybe continuing this on, looking at other surrogate measurements, maybe for this topic of hydraulic fracturing fluid influence on groundwater, but perhaps also some other analogs or to the research that I'm doing for my doctoral degree. So once again, thank you guys for letting me present from a video, and I hope all your guys' presentations have gone well, and look forward to maybe catching them if you guys can share the PowerPoints on D2L. Other than that, have a wonderful day.